Just, oops. No. be prepared, but Douglas came in and he said, what about inviting Javier?
No, we just... Good afternoon. On behalf of the Southampton Theory, Astrophysics, and Gravity Research Center, I would like to welcome you to this event. My name is Kostas Kenderis, and I'm the director of STAG, and I will be your host this afternoon. So the mission of STAG is to promote and foster cutting-edge research that goes beyond traditional boundaries. And our ultimate aim is to describe the laws of nature from the very small to the very big, from the fundamental microscopic building blocks of matter to galaxies and the universe as a whole. And we think an important part of this is also to engage the general public in what we do, to promote public awareness of what is fundamental science, and also to inspire the students of today to become the scientists of tomorrow. And as part of this mission, we organize a public event every year, which features a very distinguished guest that explores in his speech some of the most important fundamental discoveries of our times. We also run the STAG interactive workshops, which aimed at secondary school students and sixth formers. And in these workshops, we aim to explore and explain the mathematics and the physics of some of the research that we do. And one such workshop was held this morning. So this year, we're introducing a new initiative. So we're going to have some new STAG prizes. And these are aimed to celebrate the achievements of our PhD students and will be awarded to students for best publications in the research areas covered by STAG and also for public engagement. So we're delighted that members of the leadership teams of the two faculties that support STAG, the Dean of the Faculty of Social Sciences, Professor Jane Fockingham, and the Associate Dean of Academic Infrastructure of the Faculty of Engineering and Physical Sciences, are here and agreed to present these awards. The prizes for these awards will be physics books, which are signed by our distinguished speaker. So to give this, so we'll start this afternoon by giving these prizes, and I would like now to invite Professor Butler to join me. Okay. So the best prize would be the best publication in astrophysics. And for this prize, there were 3 students that were nominated, Joyce Lee, Sam Manham, and David Williams. And the winner for this prize is Joyce Lee for work on the importance of magnetic fields in the formation of stars. Joyce is currently working as a teacher at Brittany Park Secondary School. Unfortunately, she couldn't be with us at this moment, but she will arrive later. But her mother, Jenny Lee, is here, and she will receive her award on her behalf. So I'll invite Jenny Lee to come forward. So the second award is for best publication in high energy physics. And in this category, we have the following students that they were nominated: Jack Foster, Simon King, Elena Perdomo-Mendez, Hinek Paul, and Stanislav Smith. And the winner in this category is Simon King for work on extensions of the standard model of particle physics and how to test them using experiments at the Large Hadron Collider in Geneva. Simon is currently spending the academic year at the University of Padua, supported by a prestigious fellowship. And Professor Stephen King, one of his collaborators on the awarded paper, was agreed to receive his award on his behalf. So I would like to invite Professor King to... Yes, now I'd like to thank Professor Butler and invite Professor Buckingham to join me. The next prize is for best publication in gravitational physics. And in this category, we have the following students were nominated: Alice Harpel, Hinek Paul, and Stanislav Smith. And the winner in this category is Hinek Paul for work on new methods to develop quantum gravity. So I'd like to invite Hinek. So our final award is for public engagement, and for this award, the following students were nominated: Joan Garcia Tormo, Chris Marsden, Elena Permondo-Mendez, and Emma Osborne. And in this category, the winner is Emma Osborne for her outreach efforts related to gravitational wave astronomy and the activities of the Ligo and Virgo collaboration. So I'll invite Emma to come forward. Okay, now it's time to turn to the main event of this afternoon. So we're delighted to have the 2017 Nobel Laureate in Physics, Professor Weiss, delivering this year's STAG public lecture. And it is my pleasure now to invite our President and Vice Chancellor, Professor Sir Christopher Snowdon, to introduce our distinguished guest.
Well, thank you very much, Kostas. And it gives me great pleasure to add my welcome to the annual STAG public lecture. For slightly tongue-in-cheek, you may not realize it, but this is actually even more prestigious than getting a Nobel Prize, because we only invite very few Nobel Prize winners to come and give this talk. And it is my very great pleasure today to welcome Ray to give his. And I'll just say a little bit about Ray. Ray is a professor emeritus at MIT and is also an adjunct professor at Louisiana State University. He's really well known for his work on two really important phenomena. His early pioneering work was actually in cosmic microwave background radiation, which is actually close to, I'm a microwave engineer by background, so it's close to my sort of world too. And his other area, which he's probably most well known for now, of course, is in gravitational waves. And we're about to all find out, and let me say it's a great pleasure to welcome those of you from schools and colleges today as well. Gravitational waves are ripples in the fabric of space-time, and were predicted actually over 100 years ago by Albert Einstein. And you probably saw Kostas as wearing the Albert Einstein tie today to recognize that. Now, Ray was awarded the 2017 Nobel Prize for physics for the work on the Laser Interferometer Gravitational Observatory, Ligo. And by the way, you can get ties for Ligo, I understand, as well, so put your orders in now, for the first detection, actually, of gravitational waves. And he won the prize with Kip Thorne and Barry Barish, who shared this with him. Now, for those of you who don't know, coming back to the first part of Ray's work, cosmic micro background radiation, allegedly, I suppose we'll never prove it, originates from around 400,000 years after the start of the universe. And indeed, the early work done on this goes back actually to the 1930s, so not that long ago. And a really interesting area of work, which itself led to a Nobel Prize in the area Ray worked in. Ray's been recognised across the world for his really significant contributions. He holds, amongst many other awards, the Einstein Prize of the American Physical Society. And it's my very great pleasure today to welcome Ray to give the 2018 STAG Public Lecture. Ray, thank you very much.
Thank you. All right. Good. Wow. Thank you. I just hope I don't mess this thing up after that introduction, you know. But let me tell you a little. First of all, I did finally learn what STAG meant, and I did now. Many of you probably know this, but it is Southampton Theory, Astronomy, and Gravity. That's what it means. So those of you who don't know that. And I have a little story about Southampton of my own. I escaped from Hitler in 1938, and we took a boat from Le Havre. It was probably the last people out of there, and actually stopped in Southampton. And I remember that boat we were on, we stopped here. It looked pretty dreary at the time. But anyway, enough. So thank you for inviting me. It's a very great pleasure to be here. And as you hear, you'll hear about this probing the universe with gravitational waves. That's the name of this. But also, there is a group here that is part of the LIGO scientific collaboration, right here. They are members of this, and they work on waveforms that we will be detecting, and I'll show you some of that. And so this is not a totally alien thing to you here. Let me start by giving you the motivation why one bothers with gravitational waves. We had a perfectly wonderful theory of gravity. There's Isaac Newton. And here's the equation we tell everybody in high school and probably in college as well, which was Newton's fundamental contribution to the idea that gravity was something that was operative on the ground, and also it worked in the heavens, which was quite a dramatic idea at the time, that there should be some coupling between things that went on the outside and things that went on the evil earth, you see. So the thing is, this has been a wonderful relationship that has worked almost for everything we want to do. It predicts, for example, space flight. It predicts all the stuff, but it doesn't do too well with the GPS that you have on your cell phones. In fact, if that all there was, the GPS would be off by something like order of mile or so, especially when you're looking for someplace. And I'll get to why that is in a second. But the fundamental reason why it is no longer the theory that people will accept as the fundamental theory of gravity is really due to Albert Einstein. And what it was is that once you have Einstein's theory of special relativity, which was done in 1905, you have to have a way of having gravity not only work for very fast-moving objects, which that doesn't work for, but also you have to have a way of having gravitational information go from one place to another without infinite velocities, without infinite speed. And for example, you can't have the sun disappearing all of a sudden and not telling us only 8 minutes later that it's gone. It also has to have an influence on our motion around the sun that is 8 minutes later. And that was not something that's in that theory. So here then is the replacement for that theory. Now, this is a little bit of an anachronism, this picture. Einstein's much older in this picture than he deserves to be, but that's the picture everybody knows about him. But this is an equation that this is that equation. Not that I'm going to tell you everything about it, but I want to give you some feel for what that equation says, because it's fundamental to your understanding of these gravitational waves. What it says is that on the left side here, this is somehow, we'll not go any deeper to say, this expresses something about the geometry of space, the way you measure space, but also the way you measure time. This thing on the left. And this, forget about the 8 pi, that's known to everybody, but this is the distribution of energy and matter, and that somehow the distribution of energy and matter that's in the space affects the space and makes the geometry of space and time. That's the basic idea. There is no longer a gravitational force. It's been buried in this thing. And let me give you a feel for what that does. And the best thing I can do is sort of give you this picture. What this picture is, how many of you know what a jungle gym is? My God, only a few of you. Well, if you come to New York, I'll show you a jungle gym. It's a thing that kids play in, and it's a three-dimensional matrix of bars. And it's beautifully square, and now think of taking a cut, a two-dimensional cut through the jungle gym. Okay, and that's what you're seeing here. In other words, the two-dimensional cut through the jungle gym is represented by, out here where nothing funny is going on, all these squares of bars that are hanging together. It's two-dimensional. Remember, there's more of the jungle gym below you and above you, but the 2 dimensions is enough. And then you'll notice something interesting. Here's the sun. It's put into this space, and it distorts the jungle gym. It makes it curved. It curves. It makes things that were straight lines into curved lines. And here's the Earth doing its bit. It's a little less, you notice. It makes a little dimple there. And so this now is sort of a representation of that equation. It says that a flat space gets distorted by these objects that you stick into it. But there's more to it, which that picture doesn't show, which is it also changes the time that's kept by clocks. In other words, out here where nothing is much curvy, if you put clocks at all the intersection points of this thing, which is kind of expensive and you don't want to do that, but you put clocks there, they will all read the same time at the same moment of time. On the other hand, if you put clocks in here where things are curvy and near the energy source and the mass source, you will find those clocks going a little more slowly. In fact, clocks in strong gravitational fields tend to go more slowly. They do, not tend, they do go more slowly than clocks far away from these gravitational sources. And that's the thing why GPS needs Einstein's theory, by the way. See, the satellites that tell you where you are on the Earth are living at 23,000 miles away, and you're on the Earth, and that you're much further away from the Earth, so the clocks go at a slightly faster rate out there where the satellites are flying around. Okay, now in this theory, you have now replaced something. You've replaced the gravitational force with some reconstruction of what space looks like and time evolves. And then you have a wonderful statement that John Wheeler made, who was one of the originators, along with Einstein, of this theory, that the space and the time now tell matter how to move. There's no force anymore. Okay, now in this new theory, there is also gravitational waves. And what are they? Well, in 1916 and 1918, when Einstein was first, in 1915 is when he made this big presentation of this new theory. But in 1916 and 1918, he wrote about consequences of the theory. And he found that there were waves in that theory which allowed information to travel from one place to another with finite speed. In fact, these waves will travel at the velocity of light. By the way, you'll learn at the end of the talk, or sort of near the middle end of the talk, that we now know that for a fact. They travel at the velocity of light, but they do funny things. They're transverse waves. They're waves that are perpendicular. They do their dirty work perpendicular to the direction in which they're moving. That makes them transverse. And I'll show you a wave in a second. The way they're generated is by having mass that's accelerated. In other words, not all kinds of motions will make a gravitational wave. For example, a spherically symmetric collapse will not make gravitational waves. But there have to be non-spherical accelerations. I'll give you examples. One example is 2 trains hitting each other. That makes gravitational waves. Zilch, tiny, infinitesimal, but never mind, they're made. Or 2 objects going around each other in some kind of elliptical or circular motion. They make gravitational waves. So that's what you have to think about as sources. And here is now what I've got, and I'll look at this set of dots that you see here. I'll get this all moving in a minute. But right there, I can't see it so well from here, there's a dot with a red square around it. It's one of the 2 middle dots. I think it's that one. That's you. You're standing at that dot. And now let's say a gravitational wave comes out at you or goes into that picture. Here's what will happen to those dots. Think of those dots as a whole bunch of masses you've strewn around in space, okay? Not on the Earth, they'd all collapse, but they're sitting out there in space. And now what you'll notice when you look at that picture is two things that are very important. The first thing you'll notice is that there is a stretching of space in one dimension. Let's call this the east-west dimension. And when this is stretching in the east-west direction, in the north-south direction, it's doing the opposite. So it stretches, let's say, in the east-west direction, and then compresses in the north-south direction. Okay? Do you see that all? I hope that's there. You see there's that motion. And then the other one, which is the most important in terms of understanding how you might detect these waves, is to look at actually the motion of the dots themselves. So take a look. Here you are, let's say, at the center, and the two neighboring dots you have, that one and that one, don't move very much. But look at the ones that are furthest away from you. They're moving a lot. And by the way, the ratio of the amount of motion to their separation is the fixed number. That's the same in this picture at any one moment. In one case, it happens to be negative, and the other case, it happens to be positive. But it's change in length divided by the length. That's called the strain, and we'll come back to that over and over again. That's the thing that at any one moment is the same in that picture at the same moment of time. So, okay, so now a little history. The first people to actually detect gravitational waves indirectly are these two guys. That's Russell Hulse, who was a graduate student at the University of Massachusetts when this happened. And this is Joe Taylor, who was a professor there at the time. Both of them, once after they made this discovery, wound up in a very prestigious place called Princeton. But they did their discovery at the University of Massachusetts. It's a public college in the United States. I just want to make an issue of that. And so what did they discover? They were radio astronomers. And what they saw, and you had a talk here from Burnell last year, I think. And some of you were here, that the big discovery of pulsars. These are these stars which are equal to the mass of the sun about, but they're about the size of the city of Southampton, not bigger than that. So they're enormously dense. In other words, put a solar mass into a size of a thing that's about the size of a city, you wind up with the density of material being like the nucleus inside of an atom. You can't put a spoon into that material and lift it. You're not strong enough. So the densities are 10 to the 15 grams per centimeter, or 10 to 14 grams per centimeter cubed. It's just unbelievable material. And what they discovered, and actually the guy who discovered it first was a graduate student, Hulse, very much similar to the story with Burnett, was he was working in Arecibo, a detector in Puerto Rico, and the big dish that looks up, and they heard this brrrr like that. And that's about 17 times a second. I can't quite do that, but that's supposed to be 17 times a second. And what they noticed, and what Russell noticed, is that over time, it wasn't always exactly 17 seconds. 17 times a second. Sometimes it was a little faster, sometimes a little slower. And the model they made of it eventually is this picture right here. There's the pulsar making its radio pulses. They didn't know what the other thing was, but they assumed it was another object that was real close to it. So it wasn't going to be an ordinary star, because an ordinary star would completely be much, much bigger than the space between them. So it must have been another tiny star, and they were going around each other in an orbit. And that made an incredibly good laboratory for doing testing of Einstein's theory. Because, you see, what you now have is you have this object and that object moving around, and you could, by the Doppler shift, which is when, let's say, this star, the pulsar, this is getting a little troublesome. This star, when it happens to be over here in its orbit and going toward us, the Earth is right here, let's say, there's the Arecibo dish right here. And when it's outstanding, and when it's over here, it has 17 times a second. When it's over here, it's measured with a little higher frequency than 17 times a second, and it turns a corner over here, it's a little slower than 17 times a second. It's the same kind of thing that happens when you have a policeman chasing you, when you're speeding. You hear the guy with the siren, and it's a little fast when he's coming at you, and then when he goes past you, it's slower. It's the Doppler effect. And with that, they were able to get a whole huge amount of information about that system. And it was a system that was well enough isolated so that they could really use simple theory. You didn't have to use the full-bore collective body theory of everything. You could do two-point masses, which is a thing you can do in ordinary Newton's theory, but you can also do it beautifully in electricity. You can also do it beautifully in Einstein's theory. And they, among all the other things they found out about this, they plotted this curve. This was plotted many, many years later. And this curve tells you the following. This is epoch down here, starting in the 1970s, going all the way to the year 2000. This is time. and measurements they made of the following. The thing they made was a measurement of how long it took for those two objects to go around each other once. Once, every time they go around. And what they noticed is it took less and less time to make the orbit go, to make one orbit. So that's what these dots are in here. They're right on, and that line that runs through all the dots is not a fit. It's actually just a calculation when you do all the masses and calculate everything out. What would be the change in the orbit if this was radiating away gravitational waves? That was, as far as I'm concerned, an indirect measurement of the very first indication that gravitational waves existed. And that won the Nobel Prize, I think, in 1993. I'm not sure of that date, but it was of that order, something like that. An enormous piece of wonderful good luck that they found this, because it let us go on to other things. So that's the first measurement. Now, the first person who really thought that you could actually try to detect gravitational waves was Joe Weber. That's a picture of him. He looks a little nutty, I'm afraid, but okay. And he was a little nutty, but he was very, very smart and very inventive. And what he did is his idea, along with John Wheeler, was to make a thing that actually looked at that motion that I showed you in the picture with the dots. And the idea was to take a big metal bar like what you have here, and there he is putting strain gauges on that bar. That's what he's doing. He's putting objects on it that can measure the extension of that bar and the contraction of that bar. And what the idea was that the gravitational wave would come along perpendicular to this, it'd pull on the bar, make it longer and then a little shorter, at a frequency about equal to the gravitational wave. And what he wanted to do, he wanted to hear that bar sing after the gravitational wave. In other words, the way he was thinking about it, the gravitational wave could come along like a hammer and bop the bar, much like a xylophone. That was the idea. And well, there he is, and there is the tank that you put the thing into, a big vacuum tank. And to his misfortune, and that's really his misfortune, he detected something. Now, the way he detected it was really dramatic, and it's also used today. What he saw, he had 3 of these bars. He had one of them in the University of Maryland, where he was a professor. He had another one on a golf course about 8 miles away from the place where he had his office. And then about 800 miles away in Chicago, he had another one. And what he published in 1969 was a discovery of gravitational waves by seeing coincident pulses by these very far apart objects. He saw 2 or 3 a day. And that set off a revolution in physics. I mean, it's not such a hard experiment. You can see that. It's an experiment that most physicists could do if they wanted to. It's not a terribly hard experiment to do. A lot of people in the world did do that. And for example, in Britain, I have to be careful how I say this, the United Kingdom, excuse me. In the United Kingdom, the people in Scotland, in Glasgow, a guy named Ron Drever and Jim Huff, decided they would do an experiment also, like this one. And then all over the world, there were people in France, there were people in Germany, there were people in the United States, 3 or 4 groups. And the paper he published was 69. By 72, it was quite clear to everybody that there was nothing there. And that was unfortunate, and there's a lot of rancor about it, there were a lot of discussions. Weber, unfortunately, never quite admitted that he wasn't seeing anything because he says he was seeing something, and he accused people of not doing it exactly the way he did it, and that's why they didn't see anything. And that is not a good defense in front of the rest of the physics community. You have to give better defense for that. So what happened is that eventually the bar business is still going, and people tried to make better bars, so you have an idea of what I'm talking about. The best he could have detected, as far as we can now reconstruct from those experiments, is a strain of 10 to the minus 15. Now, by the way, I'm assuming that you know how to deal with numbers like 10 to the minus 15. What is a number like 10 to the minus 15? It's a number, when it expresses a decimal, you would write a decimal point, then 14 zeros, 0.000, 14 times, and then a 1. It's a very, very tiny number. It's a lovely way to talk about very big numbers and very big numbers and very little numbers by expressing them as an exponent of the power of 10 that you have to use to get to that number. It's a wonderful way to talk. I wish the press would do that. I wish the people would stop talking about billions and billions and trillions and trillions, because you never can get the language right. So 10 to the 2 is 100. 10 to the minus 14 doesn't have a name. Okay? So, okay, we're going to be using that a lot. I'm sorry, but there's no way out of it in this business. So the technique that actually made the detection is this one. And this is different than Weber. Weber is claimed, and he has, I think, thought of it himself also, but he was busy making bars. But let me explain this to you. This is an animation you're going to see in a minute. And there is a laser. It doesn't look like a laser, but imagine that thing is a laser. It's putting out light. Here is something called a beam splitter, which splits the light, so half of it gets reflected this way, and the other half of it gets transmitted that way, okay? Think of a gravitational wave coming down on this system, okay? Over here is a detector, which is where the light that results will come out. And there are a couple of attributes which I have to tell you ahead of time, but I'll come back to. We've made the animation work so that the time it takes light to go from the laser, from the beam splitter to that mirror and back again, is exactly the same time as it takes the light to go and get transmitted to this mirror and come back to here. And you will notice an interesting thing, that the light cancels as it goes to the detector. So let me get it started. That device is called an interferometer. That's the name for it. And here, wherever there's red, there's light power. And the wavy thing is the electric field that's in the light. And here you can see it getting reflected from one mirror, the other mirror. And now you'll see as they come back to the beam splitter, the two beams cancel each other. The electric fields have spent equal time in the two arms, and you get no light to the photodetector. You see no red at the photodetector. Now you start moving these masses, like the gravitational wave will, when it comes down on it, and you'll see you do get light at the photodetector whenever you break that beautiful symmetry of having equal times in the two arms. Now, is there anybody in the room who doesn't understand what I just said? Please raise your hand. Don't feel intimidated. I can't see so well against that light, but all right, nobody admits it, or it's just crystal clear. I'm assuming crystal clear. Okay. All right, good. That is the basis, by the way, of Ligo. There's no more of the physics to it. The tricky part comes now. This gentleman is Kip Thorne, who is one of the co-winners of that Nobel Prize, a very close friend, and has been much of his life thinking about what might be sources of gravitational waves. He's at Caltech, and has had a whole group doing theoretical work there on this for years. And he told us very quickly, very early, but we didn't know this, he told us very early that if you want to get in the business to measure gravitational waves, that means if you want to measure a strain, which is a change in length divided by a length, it gets a special symbol called h. That's called the strain. You've got to be able to measure strains smaller than 10 to the minus 21. That's what he told us. And so Weber was miles off, okay? And the thing was, that's a challenge. And that's what it took 40 years to do. It isn't that a theorist could say, yeah, you got to get down to 10 minus 21, we didn't know it. That was known a good bit in advance, but how to do it? And I'll say, what are the tricky bits of it? The tricky bits are these two statements right here. First is that if you want to measure a strain of 10 to the minus 21, let's start with how well you have to deal with the light. You have to, this is how much of the motion that you have to measure, how big is that delta L relative to the wavelength of the light, which is always a measure of how well you can determine the position of something with light. So it turns out you have to be able to look at 10 to the minus 12 of a wavelength of light, 1,000,000 times 1,000,000th of a wavelength, to get to 10 to the minus 18, which is the strength that we ultimately, when you convert this with a 4-kilometer system and put the 4 kilometers into the L, multiply that, and get it in meters, you wind up with a number about 10 to the minus 18. So I should have mentioned that earlier. So now comes the thing. That turns out, as I'll show you some of the tricks that were used to get that. That was already kind of a tall order for people, but it wasn't the thing anywhere near as bad as this one, which says that, and this is the reason why I would not build, and I was talking this with her a minute ago, about building a gravitational wave detector in Southampton. It's not a good place to build one. And the reason why is the ground is shaking here by at least 10 to the minus 6 meters, or again, 10 to the probably 10 times that. And anyway, you have to worry about the ground shaking in those mirrors that do the reflections. They have to be supported in such a way that they don't partake in the motion of the ground. And so that means, again, in quiet places, even on the Earth, you have to do a 10 to the minus 12 of the vibration of the Earth's surface. Right now, in this room, you're jiggling up and down by about 10 to the minus 5 meters, at least, certainly that much, because you're close to the ocean. So it turns out that's where the hard work was. And so here, let me show you quickly the tricks that are used. I know you have, within your group here at Southampton, you don't have an experimental group. So unfortunately, you're going to get it from me, okay? Yeah, maybe they know the troubles, but you're going to get them from me, okay? And so here is the way you get around. This is, for example, the first detector we built. And you'll notice something that in this picture, which you already know about. There's the laser. There's the beam splitter. You had those in that little picture of the motions. And there's that distant mirror. And here's that distant mirror. And there's the photodetector. So there's some extra things in that picture. And I'll only tell you what they do. But they are part of the way to get that 10 to the 12. One of them is you put another mirror here in each one of these arms, there and there, and you make the light bounce back and forth 3, 4, maybe 200, 300 times. That's the same as making it longer or making you interact with the gravitational wave for longer. I don't care how you think about it. And those things make these into cavities, they call them, but you make them so that the time spent by light bouncing back and forth in here and bouncing back and forth in there is very close to the same in both arms. And so again, you get into a situation where no light goes to the photodetector. So where does all the light go? Well, it turns out the light all goes back to the laser. That's where it goes. In other words, it looks like the whole system, all of this junk, all put together, when no light goes here, the light has to come back someplace. It doesn't get absorbed by the mirrors. So it comes back to the laser. And if you put another mirror in here, and that's called a recycling mirror, there's no reason to go any deeper than that. What that does, it takes all the light from the laser, manages to make it so that this is partially reflecting, so that a light that comes back out of this, heading to the laser, interferes completely with the light that hits from the laser to this and gets reflected. So there's no reflection. You have an interferometer at this point where the reflected light of the laser and the light coming back out of the interferometer interfere with each other. And that makes it so that all the light winds up in this interferometer. So you might have 10 watts of light here, you might have 500 watts of light circulating in here, and you might have maybe 300 kilowatts of light running back and forth inside that cavity. So that's part of the tricks that were pulled to make the detector work. I rather skip this slide unless we can come back to it if you have questions. What it is a noise budget for the instrument. I'd rather not spend time right now on that. I want to go forward. You can ask about this slide. It is effectively what are the noise sources that are, and I haven't described to you. But I'd rather go forward and tell you about the discovery, okay? And you can ask me later if you want to come back to that. Anyway, this is now the structure of the way things look. Where are there detectors like the ones that LIGO has? And you can see that here's the United States. There's one detector in Washington State in the northwest corner. Then there's another detector in Louisiana. But that is not the only detector. There is a detector, a large detector, but not as big. These are 4 kilometers, and I'll show you some pictures of them in a minute. But not as large. There's a detector in in Germany, which is done by which is joint between Scotland and Germany, okay? And that's been running for many years. It's a research detector, really. Then there's a detector in Italy, which is the Virgo detector, which plays a role in this, a very important role eventually. And then these are ideas that are for the future. The Japanese are building a detector inside the Kamioka mine. That's where the neutrino detector is. And there is a detector in India that's being built using a detector that was a spare detector for LIGO. Those are in the future. And I'll explain why we want all those detectors in a minute. I'll tell you now, but I'll show you more in demonstrations. The reason we want all those detectors is because it allows us better to couple gravitational wave astronomy to ordinary astronomy, because you can't tell where the sources are with gravitational wave detectors very well. I'll show you that in a minute. But first I'm going to give you a little tour of LIGO. And this is looking down on LIGO. This is now in Louisiana. And you'll see as we go on if this runs. Yeah. And this is the same thing up in Hanford in Washington State. You can see those big tubes. Those are covers for a vacuum system. The same thing in Louisiana. They're identical. Inside is this big vacuum tube that's at almost the pressure of outer space. Here's a person working like on an ordinary laser table. You have those in your labs here. And here's the control room for the system at Livingston. So it's big science, but it's not enormous science yet. It's big science. Okay. So I want to show you this only because even though I didn't show you the one that I spent all the time on because we're proud of it. That's all. And what it is the progress we made over time in the very first detector. In other words, you don't have to look at this in any detail, but you can see all these curves, and they're all dated with different dates. What are these curves? This is the strain that you could measure, and it gets smaller and smaller as you go down like this. And this is the frequency, and this is around 100 hertz, is right around there someplace. So that tells you that we're lousy at low frequencies, we can't detect much, and at high frequencies things get generally worse, and there's a best region around 100 hertz where we can pick up sources. And you can see sort of this is where we started, and this is many, many, many orders of magnitude. We got better and better and better over 8 years, and we got so good, in fact, that this curve right there is the noise curve that we had just before we went to the new detector, and there's a little place where we didn't match the theoretical curve for the detector. That's in there. But over a very, very large band, we succeeded in making the detector work as well as what Kip required of us. And and it turned out to be a very clean non-detection. That's what I wrote there. And that's very important in this business. If you know what's wrong with the detector and you can fix it to the point where you work at theoretical level for the detector, you've accomplished something very important. You may not have detected gravitational waves, but you showed people that you had the competence to go ahead. And that was the next step that we did. And that's called advanced LIGO. And there were some changes made. I won't go into all parts of this, but the very big thing that changed, and again, I'll leave much of this to questions, is that what we changed is the thing that separated the mirror, which is down here, from the ground, which is attached to these springs. So these springs are attached to the ground, and there are 1, 2, 3, 4 pendula in series. And a pendulum has this property that if you shake the top of the pendulum this way, and if you shake it slowly, the object below it moves together. Try it with a piece of string, you'll see. And then if you shake this very fast, this stands still. Okay? Almost still. And that's what the game you play here is, to get rid of the noise that might come from the Earth. And there were many other tricks. One of the other tricks was, I'm not going to go through it, is a trick that's described by that picture if you want to ask about it. What it is, the same thing, it's a very clever idea that was had by people at Stanford. And what the idea was is you use a seismometer, which is a device that measures how much the Earth shakes, put it on a platform with pushers on it, and make it so that you make a control system that makes the seismometer read nothing. In other words, here's the Earth shaking everything. You have the seismometer on a platform separated from the Earth with springs, and you push on the platform to null out the seismometer. Now that's just something, I don't know, those of you who do experiment here may want to do that too. Turns out that's one of the few things that LIGO developed that might be useful to other people, okay? And so that together with the new suspension got us this. This is the first detection. And now let me talk about that a little bit. So the first detection, this is what was seen in Livingston over here. This is time, and that's strain. And if you look at the magnitude of the strain, I don't know if you can read that number, it was right on. Kip was right on the money. This is about 10 to the minus 21. And this is the same thing, same time, same y-axis at Livingston. And let's quickly look at these two. That's junk. All that stuff is junk. That's noise. And then slowly something builds out of the noise, which you see, which is quite organized. And then again, there's junk afterward. Same thing happens here. And now you can superpose those two, and you will see something that's just entirely within the noise. In other words, you'll see that if you now translate that signal that you see in Washington State, the blue one, and translate it by 7 milliseconds. That's what you have to do. You have to translate it relative to the signal you have from Louisiana, because it takes 7 milliseconds for the gravitational wave to go from Louisiana to Washington State. That tells you it's coming from the south. And since you think it's the velocity of light, and we have better evidence for that now, but that was the first evidence we had, you have to slide to get this fit, which is the two coherent parts to be on top of each other, you had to slide one by 7 milliseconds, 7,000th of a second. So that was it. That was the first detection. And there's another way to represent that detection in terms of frequencies. In other words, when you have a time series, you can say, what is it, the function of h as a function of time, but you can also say, what are the frequency components in that signal? And this is a different representation of the same thing. What you see in this picture is frequency on this axis. And for example, right about 256, this middle C, and that's the bottom of the piano. And this is now Livingston, and this is Hanford. And here's that same time series, because this is time again. But what you see is what's new here is what are the frequency components in that signal. The brighter it is, the more amplitude at that frequency is in the signal. And then they look quite similar, and here's what they sound like. Not much, right? Boop, boop, like that. Well, okay, so then we did a trick so that you could hear a little better, which is not the way the instruments are. Okay, now, whoop, that's the chirp that comes with that signal. That's why it's called the chirp. So, what was it? And this is the other very important part, not only the technical development that was done to make the detectors work. I think, to me, this is equally important. And I want to say something about those Einstein equations I showed you in the very beginning of the talk. They're fierce equations to solve. I can't solve them. And most people couldn't solve them at the limit that was required. They could approach the solutions that we're about to see. But in the end, the way it was really done was to make a computer numerical solution of the Einstein equations, which are enormously complex, much more complex than that one line I showed you. And this happened just about at the same epoch as we made the detections. So what you're going to now see is what we think, and I'll show you more of that in a second, what we think this signal was due to. These are two black holes. In the top right corner is the time, and this is not an artist rendition, this is a computer output of what actually happens. And why I showed you the jungle gym is because this is what allows you to think about this. The colors, by the way time elapses, where the color is black, the time has gone to zero. You can do no time. And red, the clocks are going really slowly. And then these arrows indicate for you the stresses that are in this region. Again, this is two-dimensional cut through this thing. And you can see the two black holes, they're up here. That's just to show you what's going on. And they're beginning to cause really big distortions in the space and also in the time. And here they slowed the movie down so you can watch the collision of the two black holes. And you can see this is enormous curvatures. There's a storm going on in space here. It's really quite unbelievable. Here they're just about to form a new black hole. And now it becomes quiescent. There are still oscillations, which we hope to see one of these days. And then here are the gravitational waves that are flowing away from the system. And as far as I'm concerned, that's really as much of a miracle as the actual detection in many ways. So that people were able to do this. The people had tried for probably decades before that to try to get a black hole collision to work. And you got it to work almost up to the endpoint, but not to the endpoint. The velocity, by the way, of those two stars, or what's left of them, these two black holes, is close to one half the velocity of light. I mean, imagine something of the 30 solar masses going about one half the velocity of light. It's unbelievable. Anyway, right after the discovery, I happened to be in New York, and these are the two pictures. One of them is on the left, your left, is an advertisement I saw on the subway. And it says, "Scientists found gravitational waves in outer space. If it only were that easy to find an apartment in New York City with a walk-in closet." I mean, imagine this is now in a week or 2 weeks after the big announcement that we made in Washington, D.C. Some people have picked this up already. And then there's the thing on the right is a cartoon that happens to be in the New Yorker, which is a magazine, and we read a lot in New York. And that's these two birds sitting there, and one says, "Was that you I heard just now? Or was it two black holes colliding?" Okay? So suddenly, I mean, and this is something I've noticed a lot in my going to schools in the United States and talking to high schools and grade schools. I find out that when you ask in the United States, I don't know how it's in Britain, but if you ask a sixth grader, name a scientist, or even a 10th grader, they say Einstein. I mean, Einstein is sort of a piece of, yes, science has Einstein in it. And many of them know about black holes. Now, they know black holes because they see about them in the comic books. They're the horrible things that eat you and stretch you to death. I mean, so in other words, although they don't really know what these things are, they are familiar with some of the ideas. So that's why this funny discovery, call it what you like, sort of hit the public in a way that was far more understandable for them than many other things that are probably more significant or just as significant. So to me, it was a lesson that, if you actually have something that people understand a little bit, they resonate with it better than if they don't know anything about it. And that makes a big difference. Now here then is the other important things that have happened. These are now the same kind of plots as you saw before. And what is here is that this is the same, this is time again, and this is the strain right there. And what you see here is the one that we've been talking about. This is the black hole, the 30 solar mass black hole. I'll get to a little about what that blue statement is in a minute. Then right away, that December, we saw another black hole, different masses. And then we saw another one, again different masses, and then still another one. So we've seen enough black holes so that I'm no longer worried that the apparatus is making them to us. In other words, I think we can rest assured that we were not fooling ourselves. And that was something that Weber couldn't do. Now, there's an interesting little side issue, which I want to, that's this thing up here, which I do better by looking at my screen. I want to prove to you something, or show you something, which tells you something quite remarkable about the wave fronts and the physics of what goes on with these collisions. Suppose you had taken and put the two black holes, those two 30 solar mass black holes, and put them next to the Earth. Or the closest thing I would go is, let's say, to 1 AU, at the position of the sun. Well, what would you have experienced? And the interesting thing is you would, on the Earth, have experienced, with all the frequencies that are involved in that, you would have heard maybe something in your ear. The H value, the strain that you would have at the Earth is about 10 to the minus 6. That's what's on that slide. You can't imagine what 10 to the minus 6 means. It means that you've stretched, let's say you're 2 meters long. Well, not quite, but yeah, some people are 2 meters long. And then you've changed your dimension by 2 microns. You would never notice it. You would go right past you, you wouldn't even notice it. You might, as I say, you might be able to hear it. Why? Because your ears, like your eyes, are at a natural limit. Your ears are thermally noise limited at 300 degrees Kelvin. You may not know that, but they are, especially if you're young. So you might have heard something go, but that thing like that I played for you, but I don't think you would have. But the most important number is the last number of that list. What's the power per area that went through you? And that's unbelievably big. It's 10 to the 25 watts per meter squared. Now compare that to what you get sunburnt by the sun, which is about 1,000 watts per meter squared. So that's a factor of 10 to the 22 more power than the sun is putting out to bother your eyes. Unbelievable number. And it does nothing. And that tells you something. It tells you it's very, very hard to distort space. In other words, all these things, that nice things I showed you with that picture with all the dots, which are moving because of the strain, you don't get much. And you have to expend a tremendous amount of energy to get that little bit. So it tells you that's why these waves have taken so long to detect. That's another way to put it to you. Okay? So, all right. The next big event in this business was that Virgo, that's that detector in Italy, also saw a black hole. And that was very important. And that's what you see in this picture. You see the waveform and the spectrum for the signal in Hanford, Livingston, and then Virgo. Virgo's detection isn't wonderful, but it's there. And with that, you could do something which we weren't able to do before. You could localize, let's say, for example, this is the sky. And how well can Ligo do it alone? Well, it can do it as a big banana, about 1,000 square degrees of uncertainty. Just from the timing, that's all we have. You can't direct these, you can't point these devices. So you have 1,000 square degrees of uncertainty in the sky, and you go to an astronomer and say, go look for something, and they look at you like you're out of your mind. I mean, how can you do that? You can't, my telescope looks at, at best half a square degree. No, there's 1,000 square degrees of uncertainty. So putting another detector in another place and having a different set of timings allows you to come down to an area that's about 30 square degrees. That makes it a little better for the astronomers. And that plays a big role in a minute. So Virgo being on the air helps in the science dramatically. And this is the thing that it helped with. Now, we had this other event. We've seen now 5 or 6 black hole binaries. In 2017, we saw something else. And this was, to some of us, more exciting than the black holes. To me, it wasn't. I mean, we all know about neutron stars, and we knew about them from the Hulse-Taylor object that you heard about earlier. But this is actually seeing one of those Hulse-Taylor objects smash into each other. That's what this is. And you see it with the signal down here. This is one, now you've gotten, I hope, used to these frequency. This is time, and this is then the frequency content. And this thing tells you this is a very clean chirp. And let me play it for you. So you'll hear what this thing sounds like. It's very different than the black holes. That has a very long time series that even though it's quite a weak signal, it allows you to look for it because it's so long. Now, the remarkable thing of that was remarkable enough. But then it was also seen by an electromagnetic instrument. In this case, that curve that you see up here, this is again the same time axis, and this is the rate of gamma rays seen in the Fermi satellite. And here is sort of the end of that chirp, and that's what this line is. And by the way, our signals, our sensitivity doesn't extend to the point when these crash into each other. That happens at about 1 kilohertz, not at 400 hertz. So there's a little bit of time, maybe half a millisecond or maybe another millisecond before they collide with each other. And that's taken care of by putting this line in this picture. But something like 1.7 seconds after the explosion, or the collision, Fermi saw something in the gamma ray spectrum. And by the way, this is another instrument integral, which I think you guys have a part of, that integral experiment. And then there's, no, that's another experiment, no, excuse me. This is Fermi, this is another instrument on Fermi. This is the integral satellite, which also has a gamma ray telescope on it. So it was seen. Okay, that's a big step forward. In other words, that somebody else saw this as well. And then following that, the interesting thing was that Virgo, although we now know their sensitivity, did not see it. But that's very important. And that helped us narrow down where the part of the sky was, where this particular collision took place. Why was that? Because it turns out there is some structure in the antenna pattern of these things. It looks like a peanut. And the peanut happened to be just at the minimum for the peanut, happened to be where Virgo was if you pick this site of location. So here is sort of what goes on. Here the yellow guys are the LIGO sense. If you now put in the fact that Virgo didn't see it, you get this green thing. And here is sort of the error bar that's associated with the Fermi satellite. This is the error bar associated with the integral experiment. And so people said, go look at the place in here. And it didn't take very long. 6 hours later, ordinary astronomers, people who do as a business, they look at the sky, found this. And here's a really beautiful picture of it. Here is a galaxy that they knew about. And these are stars, and there's the galaxy before the event. Here's that same galaxy, and there are the same stars as here. But then there's this additional new thing, bright little object right there. They see the optical counterpart to the gamma ray burst. And that identified the place for everybody, and that made real impact on the science. Here's what we think now they saw. And by the way, this picture keeps changing every month as more information comes in. But this is what was thought was what was being seen. Here are the two neutron stars. They eventually become a black hole, but some people think there might be some other kind of star, but black hole most likely. And when the gamma ray gets emitted, you expect it to go off in this direction, but it turns out they were sitting at an angle, and that's why the gamma ray burst was not as strong as many others, but it was a short burst. And people then identified the position. And there were many, many, many measurements. In the X-rays, in the visible, the infrared, radio waves, all of this, they were not yet neutrinos. Neutrinos were not seen. But the point is, this became sort of a battle cry now for the whole field. And it's called what this slide says, multi-messenger astronomy with gravitational waves. And here are some of the things that were learned. One of the things that was learned is, and this is just a cute story, this is a periodic table which we teach everybody in chemistry and some physics and sometimes in high school. And it's color-coded. And the blue places are the places where we know that they were in existence at 300,000 years after the big explosion that made the universe. They were part of the initial explosion. So hydrogen and helium, a little bit of lithium, I mean, all the very light ones. But the blue things mostly, those were part of the Big Bang. Then people never were able to get the rest of the elements. In fact, that was the big game that Gamow played after the war, after the Second World War. He thought you could build this whole table by just looking at the Big Bang and seeing, but it turns out they failed. They failed to go past boron. You can see. And so up in the corner they began to realize, and this was realized here by Hoyle and others, that the stars, when they have supernovae, which are stars that have ended their lives and they blow up, and inside the stars, they're cooking up all the other elements. Well, they don't get all the other elements. And those ones are the green ones. The ones that get cooked up in supernova are all the green things. And lo and behold, some of our favorite things like gold and platinum and, well, not so favorite, uranium and radon and all those heavy things are not made that way because there are not enough neutrons to do it. And it turns out what was discovered by this whole process is that you make most of the heavies, the things that are purple in this picture, come from merging neutron stars. And that was people had thought of that ahead of time, but it was really identified. And now, to me, there's still more to be done, but we'll get to that. The thing is, what was seen is, I thought when they first did this, and I wonder how many of you who know about this thought what I did, that they actually saw the lines from gold, and the actual spectral lines from gold and platinum and tungsten and so forth. They didn't. The reason why they didn't is because when these two neutron stars have collided together, everything is moving close to the velocity of light. And the Doppler broadening is just enormous. So you can only see opacities. You can only see that things are a little opaque at different wavelengths. And nevertheless, you can pull that all together and establish what I just told you. The other interesting thing that came out of it is just a side issue, but it's very important and tells you a little bit about foreboding what the future might look like. This is a curve for experts, but so don't mind if you don't understand it. But I will try my best. What it is the redshift of the galaxies. That's on the bottom axis. And that's the fact that we now know the universe is expanding. Everything is moving away from everything else, and there was a big explosion. I've talked about that already. But now you can actually get measurements of that velocity of the explosion. And in fact, you can find that the further something is from us or further anything is from anybody else, the faster things are moving away from each other. So as you go to bigger and bigger distances in the universe, the relative velocities between two objects are getting bigger and bigger. And that's what the theory of the Hubble constant is. And that's what they're talking about here. That's this thing down here. And the blue line, which is this one, yeah, that line, and then there is a sort of tan line that comes up, are two discrepant but not very discrepant measurements of that constant. And they differ by enough so people have gotten very excited that something may be wrong in our current model of cosmology. To me, it's a triumph that they're that close, but never mind. And, but then here is this curve that you get from doing the following. That's what you get out of that one neutron star collision. You can do something very elegant. You can use those two neutron stars, have them collide, measure the strain on the Earth. You know the masses of the stars, and you also know what galaxy it was in, because the radio astronomers found what galaxy is. So you get what's called the redshift, and you get the distance together. How you get the distance is Einstein's equations will tell you what you should have gotten for the strain for those two neutron stars once you know their masses. And now all you do is you measure on the ground, the strain is 10 to the 20 times smaller than what you calculate. We're that far away from the source. That's the way you get the distance. And so all those things are consistent with each other, and they sort of lie, as you can see, they don't disagree with the other measurements. And they might, if you do this with more of these things, and we fully expect to be able to do that, we will have a completely different way with gravitational wave astronomy to measure dimensions of the universe and things in the universe, what's called the cosmological parameters. So now, a few more slides. This is, I don't want to spend time on that. Again, this is the same thing that goes with that other picture. Let me go by it, and if you ask, I'll come back to it. But what it is that it says, what is the progress we hope to make? I'll say that to you in words. Right now, we're not yet at design sensitivity for LIGO. The current detector is not sensitive enough as it should be based on our calculation for how sensitive the detector should be. We have about a factor of 2. And when you get a factor of 2 improvement, you get a factor of 8 increase in the rate. Why is that? Because the waveforms you measure And if you can improve their precision by a factor of 2, you're looking twice as deep into the universe. That's linear, twice as deep into the universe. However, how does the number of, what's the volume of the universe? How does that change that you can look into? It goes like the cube of the distance that you can look into. So if you have 1 source per month, now and you improve the sensitivity, you will get, by 2, you will get 8 sources per month. And that's a game that you can play with this thing all the way out to the edge of the universe. And so we're clearly trying to get to design sensitivity, and we have much motivation to get better detectors, and both in Europe and in the United States there are, and on the bottom of that graph, I won't go into deeper than that, there are plans for getting another factor of about 30 in sensitivity. So cube that, and you'll see this is, you're talking about events every hour. So that's something that people are planning and thinking about. Here's the reason why you want to improve localization. What happens if you start increasing the number of detectors? And here's a picture of the sky. And this is a picture of the sky with Hanford, Livingston, and Virgo. And these are the sort of uncertainties for a particular source. You can see these uncertainties in the sky, big bands where we don't know exactly, with those 3 detectors, where the sources are. If you add LIGO India to it, you can see that the error bars, the little uncertainty circles, get very much smaller. And that's the reason for pushing hard to get other detectors on the Earth. And this is my last slide, and let me end by telling you this is really where the field is heading. So this is a little complicated. On the bottom is frequency. So right here is 10 to the 4. I see better on the screen, so I have to look there. And then about 10 to the minus 16 over here. Or in terms of periods, this is sort of periods from a thousandth of a second to a tenth of a second in here. And then here is periods of the age of the universe right there. And these are years and so forth. So these are different projects, and these are the strains that they will be sensitive to. For example, the bottom here is 10 to the minus 25. The very top is 10 to the minus 5. So let me talk a little bit about these different projects for you. The one all the way on the right, the high frequency one, is LIGO and Virgo and all the things that are being planned on the ground right now. And also the improvements that one thinks about. And they have certain classes of sources, like these compact binaries that we were talking about, and other kinds of sources. We're looking for periodic sources, for example. Then there's something called LISA. By the way, the Scots, again, Great Britain, including Scotland, is very much involved in this experiment. So is the United States, but not as much as it should be. And what happened there has to do with money, as all things do. And the thing is, what is this about? This is called the LISA project. It's going to look at sources that are a few hours to minutes. That's where their band is. It's a completely different set of physics that goes on, and astrophysics that goes on with the shorter wavelength things. And there you're looking at, for example, massive black holes colliding, the ones that hold galaxies together. You know, all of us, you probably know that our galaxy has a 10 to the 6, a million solar mass black hole sitting smack in the middle of it, eating away. I hope you know that. And anyway, so but there are galaxies with 10 to the 11, 10 to the 12 solar mass black holes, especially in the early parts of the universe. Now, those will be seen gangbusters. You'll see those with LISA. You'll also see white dwarf binaries, ordinary white dwarf stars, stars that are held together by electrons being pushing apart. And they are all over our galaxy, and you'll see the radiation from them. And you can do very precision tests of Einstein by letting small objects fall into big black holes that we have. So it's a very important mission to do, and it's about as old as LIGO in the thinking of people in the United States. I mean, this was, we started pushing for LIGO in 74, 73, and we started pushing for LISA in 75, about 75. And it's been going on for a long, long time. And now there's a very big, it's now being run pretty much by the Europeans, the European Space Agency. Then there's a project that's already, by the way, when might they fly? They hope to be in business to be able to fly the LISA sometime after 2030. That's, for you young people, that's not so bad. For me, that's a kind of serious problem. Not that, look, no. I'd love to see this happen. Then there is a project that's now ongoing, which is to use pulsars, the pulsars we have in our own galaxy, as clocks. And the idea is very pretty. It's a pretty idea. The idea is, for example, if our galaxy is continually being suffused by gravitational waves that are coming through. And you look at a bunch of pulsars that are going fast. We now have pulsars that take 600 times a second. Imagine a star spinning at that rate. It's sort of unbelievable, but that's what they do. 600 times a second, and up here there's a whole bunch of them in the north, and there's a whole bunch of them in the south, and you look at them, and then you look at them as a pair, the north and south guys, and the north guys and the south guys, and then you look at the east guys and the west guys, and look at them as a pair. You could tell if a gravitational wave is coming through with a long period, a period of years, coming through our galaxy. Why? Because the north-south guys will all go a little faster, let's say, tick a little faster, and the east-west guys will tick a little slower. It's a neat experiment to do. And from it, you can get an idea what might be the strain and the gravitational waves that come from way, way long ago, not necessarily from the Big Bang. That's unfortunately, I don't think they're anywhere near enough, sensitive enough to do that. So then there's this fourth experiment, which is now going on right there. And you have some interest in this through your own groups here. I will only describe this to the extent that I can without, you can ask me questions more about it. But what this is, a cosmological cosmic background of gravitational waves. In other words, there is various theories of cosmology which say, besides making the 3-degree cosmic background radiation, which is that 2.7 Kelvin radiation that you can hear on a FM set, if you go between FM stations on your FM radio, or look off band on your television set, you will hear a noise, crackling noise. About 5%, maybe 10% if you have a good set of that noise comes from the explosion that started the universe. Okay? Now, and that's been discovered, and it was a very important piece of cosmology in your epoch. On the other hand, there should also be, especially if certain theories of the initial beginnings of cosmology are right, and there are people here working on those theories, and other people in other places working on it too, and they predict that there should be a gravitational wave background that comes from the quantum fluctuations of the very earliest moments of the universe. Quantum theory comes into this. Unbelievable. Quantum theory should be something, you already see it in the structure of the cosmic background, in the structure of it. But here you will see it quite directly in the gravitational wave background that might come from it. Now, it turns out that background is at very, very low frequencies. As you can see, 10 to minus 16 hertz. So no detector that we can make will look for it. You can do a clever thing. You can look at those density fluctuations that you get in the early universe, the same stretching and compression that I showed you in that picture with the dots, will also occur in the plasma of the early universe due to gravitational waves that had been generated before the plasma was generated. And they then will have places where it's a little hotter, a little colder, and there will be patterns of that radiation which cause the radiation to have an arrow. It'll be polarized. And you can look for the polarization of that radiation, of the optical and radio radiation. And that polarization, it will be due to the primeval gravitational waves. That's as far as I want to go. And people are looking for those patterns. They're called B modes, that's the fancy name for them. But there are certain spiral patterns of the polarization. And my prediction is that there will be either a detection of these things or a very interesting upper limit within the next 10 years of that. So that's probably the most interesting source you can imagine. Thank you.
For this very interesting talk. In a minute we're going to have a Q&A session, but first I'm going to present you with a little present to remember this event.
Oh wow, look at that. Thank you. Oh my God, thank you.
Okay, so now we're going to start a Q&A session, and afterwards, around 4 o'clock, we're going to exit to refreshments. So there are also poster sessions for some of our PhD students, which showcase the research done here by STAG. So who would like to start? Yes. Just wait for the microphone.
I'd like to see who it is. This light is a pain in the ass, I have to tell you.
Yes.
Who's asking the question?
Yeah, it's over there. It's here.
Light.
Well, I can't hear you. I'm sorry.
Sorry. Do gravity waves have any effect on the wavelength of light?
I still don't understand. What is he asking? I'm
Do
sorry,
the-
it's my ears, not you.
Do the gravitational waves have any effect on the wavelengths of light?
Yeah, okay. I see. Thank you for that question. I'm sorry I didn't quite understand it. And yeah, the question he's asking is actually a question that caused this technique, to be never funded until too late. Okay? Let me tell you what the reason is. The question he's asking is a really profound question. And it has to do with the fact that the same kind of trouble that Einstein got into when he made endless mistakes of his own in trying to apply his own theory. I'm not blaming Albert for that, but I'm blaming all of us, because when you make a theory that is coordinate independent, which is what the general theory of relativity wants to be, you should be able to use any coordinate system to express your physics in it. You can't necessarily believe the result that you have. You have to find an invariant way, and I'll get to answering you in a second, but that's the problem. You have to find an invariant way, a way that ultimately everybody has to agree on, independent of the coordinate system, that the effect exists. And now what he's referring to is the following. I'll give you the conundrum that is associated with that question. The conundrum is, people said, well, you can't measure gravitational waves this way. Why? Because the wavelength of light will get stretched the same way space gets stretched. That's the question. Isn't that the same? Yeah. That was prevalent everywhere. Well, it turned out you get into trouble if you do that, because you are mixing up two coordinate systems when you get into that kind of statement. And it turns out they cancel each other. Yeah, but it gives you a nonsense way of doing it. Let me give you 3 ways you can look at gravitational waves, but do not use them in any independent way. They have to be dealt with independently of each other. The first one is, and this is the one Weber used and Wheeler used, which I didn't like, was there are gravitational waves, and what they do is they make a tidal force that pushes things apart and pulls them together. There is no curvature in space. You don't even think about it that way. Think of it as another tidal force. And everything else is Euclidean. That's one way you can certainly get an answer. You don't get black holes well. You can't get strong gravitational fields well. That's enough. Okay. That's one way to think about it. Under those circumstances, you could lose light and it wouldn't matter. The next way is to say, okay, let's make it so that there is no gravitational force. That's a different metric. I mean, the metric's the same, but a different coordinate system. And you say, okay, the propagation speed, the coordinate speed of light changes because you have changes in the geometry along the path. And that then, but the masses don't move. The masses stay at the fixed coordinate. That gives you a consistent picture also. And then the third way, which I think is the most pretty way to do it, and those of you who like to play with mathematics, try it for yourself, is yes, there's a direct interaction of gravitational waves with electromagnetic waves, which actually puts sidebands on the light. In other words, you can propagate an electromagnetic wave at one frequency, pass it through a gravitational wave, and what the gravitational wave does, it adds you're an electrical guy, so you know. You put FM sidebands or phase modulated sidebands on the light. What are those? Those are little tiny sidebands whose amplitude depends on what is the strain in the wave, and the frequency is different than the main carrier frequency by the gravitational wave, on plus and minus omega gravitational around the carrier. And that, to me, is the neatest way of doing it, because you don't ever invoke anything but things that you already know very well. So that's my best answer to you. And the people who do it wrong will do it wrong by mixing coordinates. I'm sorry. Yeah.
Okay, any other? Yes, one up there.
Because they are waves, are they reflected by any other entity? And if so, what object?
Just saying, he was coughing. I can't hear you. Say again, please.
Because these are waves, are they reflected by any other object? And if so, what properties should the object have in order to be imaged with gravity waves?
Okay, stay standing up, because I want to make sure I understood you. You're asking what might scatter gravitational waves. Is that the question you're asking?
Yes, for imaging.
Okay, right. And so let me say a little about that. That's, again, a very interesting problem you can do for yourself. You don't have to accept my explanation. And what you do is do it first in electricity and magnetism, okay? And calculate the scattering of matter, the scattering of an electromagnetic wave by intervening matter. And how do you do that? You calculate the dipole you induce in the electric dipole that you induce in the molecules that are in the way, and then you look at what they re-radiate, okay? And there's a forward term that looks like an index refraction, and if it's not organized right, the gas is all in different places, like in the blue sky, you get scattering all around. That same process works for gravity, of course. But the problems are the numbers. It's not that the idea doesn't work. The problem is now you take and let this gravitational wave propagate through matter, and that induces, let's use the tidal way of thinking about it. That induces motions in the matter, which are quadrupolar, pushes matter apart this way, pulls it together. You calculate the quadrupole moment of that, in other words, how big a source of gravitational waves it is, and you find out you're talking about a scattering of 10 to the minus 40, 10 to the minus 40 for typical kinds of things. Of course, it depends on the mass, but the cross sections are so small that you can take gravitational waves and send them through the whole universe, including the very beginning, and never see that scattering. So we look at the gravitational waves as though they are penetrating, beyond belief. It's also another way of saying why they are so hard to detect. They don't do anything. Yeah, sorry, but that's the best answer I can give you. Yeah.
Yeah, there was another one to the right.
In a similar vein, does that mean gravitational waves, do they not lose energy?
No, that's not true. What he's asking is, do gravitational waves lose energy as they propagate? Well, there are two ways of talking about that. If you integrate, like you do with light, and you have an intervening medium and it's not scattering, if you take light, you find out if you integrate the light over all the places it can go, and ask how much intensity is over every little piece of area all the way around, you don't lose energy either. And that's what you have to do. On the other hand, if you look at how much energy there is per centimeter squared of light, it's getting smaller and smaller as you get further away from the source. And that's certainly true in gravity also. In other words, the geometric spreading out of the beam certainly exists in gravity as it does in electricity and magnetism or acoustics. So it gets weaker, yes. But if you integrate over the whole sphere that the light is going into, you don't lose energy into something nebulous. It just gets diffused, that's all. Yeah.
Yeah, one over there.
Will what you've done give us more insight into dark matter?
That's a good question. He's asking whether doing this kind of astronomy with gravitational waves will tell us better what dark matter might be. I've looked at that somewhat. I can't be honest with you and say it will do something, but let me tell you what kind of things have to be so that you would get something out of that. It might be that LISA, I don't think, and again, I'm guessing here. I don't know how to do better than guessing at this. I know it's terribly hard to already do measurements of the dark matter density around. You see pretty much, I don't think it'll add much to what people are doing now, but I'll tell you the idea in a second. What's being done now is people are looking at clumpiness, the clumpiness of the dark matter in lensing experiments, and experiments where you are looking at the light from a star or galaxy, and you'll notice that there's lensing done by the dark matter. And that gets you some feeling of the structure of the dark matter, not on what it is, but what the density and the size of the objects are, the clouds of dark matter. And I think there may very well be, not for LIGO, because I don't think we have the chance, but for LISA, they might be able, and somebody working on this thing should correct me on this. I know you have people here thinking about this, is that there might be clumpiness in the dark matter when they start looking carefully at the propagation, and they will be able to do the propagation of some of these very, very distant sources, and see if they have a phase fluctuation due to the fact that they're passing through different parts of clouds of dark matter. I suspect something like that, but I don't expect that we will actually detect the dark matter radiation itself. The fact that it's being accelerated. I don't think we'll see that. LISA might have a chance, but it's very unlikely. So I don't expect we're going to learn much unless we learn something about cosmology in its entirety, which I hope we will learn. For example, I'll give you a thing that might be important. That discrepancy that's now seen between the Hubble constant for supernova measurements and cosmic background measurements. It'd be kind of interesting to see how the gravitational measurement of that comes out and see if it can be explained by a decay of dark matter, for example. I don't know. I think it's going to be some part of the cosmological puzzle you'll be able to solve better because you have things with a completely different systematic error source than the things you do optically. But that's the best I can answer you. I can't pick the problem and say, where is it that we're going to get something from dark matter? I think we have more to say about dark energy. I think that, but I think that may very well happen before we get to the very big experiments we like to do in the future. I think people are going to learn about the acceleration of the universe at a z of 1, at a redshift of 1. They'll probably learn about that from all sorts of optical and radio measurements that are going on or going to be going on in the next 10 years. I think, and then we will add to that because we will be measuring all these black holes all the way out to the beginning of a z of about 30, a z of 40 even, way out there from the first stars get made. If we build the detectors, and I'll talk about that more tomorrow for the physicists. But the thing is that the ability to use the black holes as an indicator of what the universe is up to at very high redshift, very high distances, will have impact. And it may have impact on the dark energy and the equation of state of dark energy. But I don't think we'll have much impact on the dark matter, not directly. I'm sorry, I just don't know any better. Yeah. Yeah.
There were a question back there.
I was going to say, you talked about the space-based interferometers and larger detectors, because at the minute our capability is pretty limited with LISA. Can you foresee in the future any larger interferometers being built in space?
Well, maybe I'll quickly show you that slide. Isn't that maybe what you want me to do? Here. I mean, this is now for specialists more than, I didn't want to do it for a general audience because it gets kind of complicated. But what's in this picture is, this is where LIGO is now. This is, by the way, this is H as a spectrum, H of per square root hertz. This is frequency, there's 100 hertz again about. And so what this curve, forget about that one, that's Virgo, and they are now better also. But here's LIGO as it was during the last run, and we're about to improve things so that we're getting down to here. Sorry, not there. Yeah, right there, that. And so that is where we should be. That's the advanced LIGO design. And that's what we hope to get, maybe not this go-round, although we're making improvements in the apparatus. Let me be absolutely frank with you. We never have quite understood yet the reason why we have not made design sensitivity in advanced LIGO. We don't know it as well as we did in initial LIGO, which is the one you saw with all those curves that I showed you. We really understood that instrument after a while. We still are not at the point where we really understand this instrument. And we made a lot of changes this year. We'll hope that we get down to design, but it's not promised yet. And we hope ultimately to get to design. Maybe we have to do that within the next year after this. Then there is A+, which is this thing which is here. That's another thing that's done in the 4 kilometers. And these are big factors for rates, but they're not big factors for sensitivity. You're talking about factors of 2 or so. Then the plans for the future are, and I want to really stress these two things here. Here is a curve for something that might be done in the Einstein telescope, and that's a European idea. I won't go into what it is. And here is an American plan that is a little different, slightly better sensitivity. Well, these are all ideas for the future. And I will tell you what's the trouble with both of them. They cost a fortune. Okay, there's not been a real costing of those things. There are very clever ideas involved in them. But my guess is we're talking about $1 billion at least for each one. And that's big money. And that's not something you can get without a lot of rigmarole. We already had enough trouble getting LIGO going. So I expect that if the field advances the way I hope it does, and there really is a battle cry to be able to look at, and what's the significant point, and it's not a childish point. The significant point is that those advances will allow this field to go and do cosmological things. That you can't do with the 4 kilometers. These are things which are bigger than 4 kilometers and they're expensive. So I'll talk a little more about tomorrow what some of the science might be that you could do with Cosmic Explorer, for example. Let me blunt and tell you what that idea is to make something 40 kilometers, an L of 40 kilometers on the ground. The Einstein thing is a thing to make a 10-kilometer equilateral triangle buried somewhere in Europe. I mean, that is an idea that was thought about 10 years ago. It may be no longer quite the relevant thing, but they're going to do something in Europe which is such that Europe is along with whatever the United States does. I'm sure of that. So, but also those things are things that bring the field, especially black holes and neutron star physics, and some things we don't know about yet, but certainly those two will go into those detectors and be able to get to high values of Z. So that's the future, but it's expensive.
You mentioned earlier in your talk about primordial gravitational waves and how they'd affect the cosmic microwave background. Would the sources of these gravitational waves, would they still be black hole mergers, or would there be more different processes?
Yeah, that's a nice question. Thank you for that question. All the questions are good. I'll tell you, they're wonderful. So the question you ask is, where might this primordial background come from? Well, you ought to talk to this gentleman. He has one idea. And there are others, but the thing is that most likely, let me be absolutely blunt with you. There is some speculation that there are primordial black hole pairs. I rather doubt it, and I'll tell you what makes me doubt it is something from one of my colleagues, Paul Schechter at MIT, who gave me a conundrum that you have to figure out. He said and I know the proposal has been made by people all over that maybe you can solve the dark matter problem by letting them be primordial black holes, because you don't need to have a star to make a black hole. That's important. They can be geometric entities that don't start as a black hole that collapses, as a star that collapses to being a black hole. That's not necessary, because in fact the black hole loses the identity of what it was pretty much completely, although I know people place bets on that, but that's another story. So what happens is, yes, it could be black holes, but I rather doubt it. And more likely, what is the explanation is that they're not black holes colliding, but rather that in the very earliest phases, what some people call inflation, this is before the Big Bang gets really formed and makes a hot blob that then goes into the universe, we know that there are several ideas, one of them represented here by holography in a way, and another represented by people like Alan Guth and Steinhardt, that you have started the universe with an expansion that is unbelievably fast and has a particle that is a particle like a particle you might find in an accelerator. And this particle is responsible for the very fast expansion and is all quantum theory at that time because it's so small. And so when you start looking at what the quantum theory has for an organized system at that time in the history of the universe, you find out it has many, many states. And that's certainly true in the holography thing, but it's also true in the other model. And those states represent different accelerations of matter as they go from one state to another. So it turns out there are sources in that expansion, in that very, very fast expansion, driven by quantum pressure, if you want to call it that actually make gravitational waves. So they are before the universe gets hot. And so those are the equations, and there are calculations for how big those fields ought to be, based on, in part, what is the current measurement of the anisotropy itself. I mean, what the distribution of matter is in the universe now. Looking at where the galaxies are, you can get an idea what those represent, those quantum fluctuations. Because the dark matter made them, those density fluctuations that you see. So that's already representative of what might have been the case during that very, very early phase of the inflation. And a lot of people, including here, are thinking about how to correlate those things. So yes, there is a great expectation to hope to find gravitational waves from that epoch. Let me tell you about the experimental situation as a physical measurement where you measure it. The only thing we have right now is this business of looking at the effect that has on the cosmic background radiation, namely the polarization patterns of the cosmic background radiation. That's something which is within the next 10 years. On the other hand, people have already thought of how you might make an actual measurement, a direct measurement of that gravitational radiation. It was not in that picture that I showed at the end. This picture here does not have that. Why? Because it's pretty damn speculative. But yes, and there are people who have thought about this, and if you're interested in finding out about this, go to the web and look up Big Bang Observer. That's the name of the project. Big Bang Observer. And you will find out what you have to do to get into the regime of sensitivity to be able to measure the high-frequency tail of that initial quantum fluctuations. They should still be there, but they're remarkably small. And that is it's a project that's orders of magnitude more difficult than LISA. Has to be done in space. Effectively has to take LIGO and put LIGO into space with all the bells and whistles of all the high sensitivities and so forth. You would look it up and you'll see it's not something you tell NASA that you can do tomorrow. Okay. Yeah.
Any other question? Yeah, there is one over there. Yes.
Where are you? So I know.
Over here. My question's linked to the slide with the animation with the two neutron stars orbiting each other and then combining to become the black hole.
The what?
So
you referred to a slide. Which one?
The animation of the two neutron stars.
Okay. All right. Which version of it?
If you keep going. Keep
That?
going.
No, that's not new.
The animation, you have the animation where they're going around. I think it was.
The neutron. The animation that's of not neutron stars. Those are black holes. This thing, yeah.
Yeah. So
Okay.
when they combine to become the black hole, instead
Yeah.
of having the holes sort of going down through the space-time plane, whatever that is, it shoots up. And I was just wondering what that is.
Oh, okay. Yeah, you'll see it again when we get near the end of this. Yeah, I mean, what is that? Those are the distortions in space, the curvature that's generated. You're talking about the fact that there looks like water waves in space. Is that what you're talking about?
Well, no, what I'm wondering is why they go from one direction to then shooting up. Like if we just play this out, I'm not sure what happens.
I know you're talking about the very end when they come together.
Yeah.
And something comes up, but there's also stuff going. Those holes are deep as hell.
Right.
Okay, it goes in both directions. I mean, So right there, that thing that's coming up on the right and left there.
Why does that happen?
Why does that happen?
Yeah.
I can't tell you that. I mean, it's not going up and down. You have to remember, but these are measures of the curvature of space. So it's really, I think that's a little bit of the fake of me having told you about the jungle gym. See, the jungle gym, the curvature is represented by a dimension which shouldn't be there, the z dimension. It's the same problem here. What you do is you find out that the space is extremely curved. And how do you do that? I can tell you how you do that. And I learned it when I tried to teach general relativity to people. That's the only way I could understand the damn thing. Was what you do is if you want to know if you're living on a curved space, and that's what you would do, you still might be in a place where things are two-dimensional. That's not the problem. What you do is you take a vector and make it travel along what are called the geodesics of the space of the shortest distance in space and time along in the space. And on the Earth, for example, if you only look at the surface of the Earth and not the 3 dimensions, just look at the surface of the Earth. The thing that airplanes fly along, they are great circles on the surface of the Earth. They're not straight lines, okay? Because you can't go through the Earth with an airplane, okay? So it turns out that we know then that we live on a curved space by doing the following kind of measurement. You start with a vector and make a tangent to one of the geodesics, like take a start at the North Pole and start at the North Pole, take the vector and follow it and keep the angle between the vector and the geodesic the same. So what you do is you crawl along the surface of the Earth from the North Pole to the equator. Then you go on to a great circle that goes around the equator. Go around like that. And now this vector is always pointing at 90 degrees. You come over here, let's say 10 degrees over from the way you came down, and you go back to the North Pole, always being tangent to keeping that angle fixed. And you find out, my Lord, the two vectors, you've done nothing, but the two vectors are at an angle to each other. That tells you live on a curved space. That's what that is the intent of. Those pictures tell you that if you had done that experiment locally, you would find that angle bigger and bigger. That's all, as that height, that angle relates to the height of those waves. And that's as far as I can tell you what it means. Okay, why that happens, I don't know. The curvature is getting very big. Gravity is getting stronger and stronger when these things come together. That's the best I can do for you, really. And it's not a good explanation, I realize. Okay.
Hello, Professor. My understanding of LIGO is initially began with that the probability of can create gravitational wave is very small, such as the supernova explosion and the emerge of black hole, something like this. Also, the amplitude of gravitational waves is remarkably small, as you mentioned before. So, how LIGO can amplify the gravitational wave?
How what?
How LIGO can amplify gravitational wave?
We don't. Or how do you amplify them?
Yeah,
okay,
apart from interference.
Okay, we don't amplify them. Right? We can't do that. We can't amplify them. It's out of the question. You mean make the gravitational wave bigger? No, we can't do that. But we can do things to make it so that what we're fighting all the time isn't to try to make the gravitational wave bigger. What we're finding, for the big fight all the time, is to use the gravitational wave that comes in at a strain of 10 to the minus 21. You're not going to change that number, 10 to the minus 21. You can't change that. But the thing you can change is the noise in your instrument. Okay? And what we do is, and I can tell you reams about that, but you'll get bored silly about it, was that we do all these tricks to improve the phase noise, the noise that is the ability to make a measurement of the phase of the light. There's a lot of noise in that, and we try to reduce it. We're even now beginning to use quantum theory of light to do it. It's called squeezed light, light that hasn't got a standard Heisenberg limit in phase and momentum at exactly the same frequency. Turns out we have ways of doing that. That's a trick. Another trick is, so we have tricks. We use more and more light. And the more light you use, the better you can read the fringe. But that isn't our biggest problem. Our biggest problem is that things are shaking all the time. And now we're at a limit, in fact, in the detector that we're about to, in fact, we're very close to the limit where the Heisenberg microscope, and I'll explain that in a second, limits the measurement. Let me explain that to you. It's already quantum theory. In the end, I can tell you the two things that determine our sensitivity are the quantum mechanics and something called the Newtonian gradients. I'll get to both of those. So let me start with, sit down because you're going to get tired. The Heisenberg uncertainty is real simple. You've been taught quantum theory somewhere, maybe you haven't. But there's this wonderful way of getting the uncertainty relationship, which is that if you try to measure the position of an electron very carefully, you will louse up the measurement of the momentum, okay? Or if you measure the momentum very carefully, you louse up the measurement of the position. That's on many textbooks, and it's a wonderful example of what one of the problems are when you have to deal with quantum theory. We have exactly the same problem with these 40-kilogram mirrors. These mirrors are 40 kilograms. And we try to increase the light. More light allows you better definition of where the mass is, because it makes you have more and more light to measure the position, so you can measure smaller and smaller phase shifts of the light. And that is wonderful, but it causes a problem. All that light that you're using pushes the masses around. It's the same problem. And the mass then gets kicked around by the momentum noise in the light. So there you are. That's the Heisenberg microscope on a macroscopic scale. So, and that's one thing we have to fight. Now, we've got some very elegant ideas how to get around. You can't get around that delta P, delta X is always of order h bar or larger. That you can't do. But you can use tricks. And one of the tricks is that at one frequency, the ability to measure the phase of the light dominates the noise. That's at high frequencies. And at low frequencies, what screws you up is the fact that the mass is getting kicked around. And so what you can do is you can change the noise in the light. You can make it have less amplitude noise at low frequencies, which pushes the mass around, and lots of phase noise. Phase doesn't have to be so well defined. And then at high frequencies, you can get a lot of amplitude noise because you're insensitive to the amplitude and make the phase noise much smaller. And that's called tailoring the quantum state of the light that is in the system. So that's one trick. And that trick we have to exploit, and with more light, all of that. Now, the other one is a stinker. This is the gravity gradient noise, and that will set the limit for how well you can do measurements of this on the ground. It ultimately says you're going to have to do really big advances in this field by going into space. And what that is simple. Although we can do everything in the world to get rid of the seismic motions, let me remind you what the seismic motion is. So seismic motion is you're shaking up and down here because the water waves are hitting the shore. That's one of the reasons you're noisy here. Well, you can sense that. You can measure the amount of ground motion by the fact that you can use all the stars in the universe and use them as fixed objects and measure your motion with respect to the fixed stars. That's in fact F equals ma, the thing you learn in Newtonian physics. You can always tell if you're being accelerated with respect to the fixed stars. So we do that, and you can do that very, very well, and you can do that better and better the more technology you use. And that's all the different tricks. But then you're stuck in the end with one problem you haven't been able to deal with. And that is the same thing that makes the ground accelerate, that you can make your motion with respect to the fixed stars about, causes another problem. The other problem is that these waves in the ground cause density changes in the ground. They propagate. So here's this mirror right there. And this mirror is sitting in a wave that is compressing the ground here, expanding it, compressing it. That, because a higher density of the ground over pulls the mirror over, just by Newtonian gravity. That disturbs that mirror, and there's no way to stop that. You can't put a block in, okay? So you're stuck. And it turns out the atmosphere does the same thing. The noise of the density changes in the atmosphere are much larger, but the density is much smaller. So there are two sources of gradients of density in the ground and in the air, which actually have Newtonian forces that pull on the mirror. And those cause a real problem. And that's why people, for example, in Italy want to build their system in the ground, underground. They think they're going to get less gravity gradient noise there. They may. We think that may be true, but but in the end, you don't gain quickly. They will do it. We'll find out. The Americans, on the other hand, think that it's hopeless, and they're not going to try to bury this because it costs so much money. You see? So you can see the differences in approach. So those are the two factors. The one that's really the most important one is the gravity, is the quantum limit. And the other one is the gravity gradient limit. Now, there may be ideas you can think of where you measure the pressure in the atmosphere everywhere, and you measure the motion of the ground's density everywhere, and you can correct a little bit the motion that you might impart to that mirror. People are working on that. But I don't think it's very promising. Okay? Yeah.
Any last question? You can ask the last question.
When you look at the principles behind the Michelson-Morley
I could not understand you. Sorry.
So when you look at the principles behind the Michelson-Morley interferometers and the Ligo interferometers, it's sort of quite a similar idea. Was there a link between developing Ligo and looking at the ideas of the Michelson-Morley interferometers?
I'm going to have to ask him what you said. Stay there. What did you say?
Yeah, so the questions about the Morley interferometer, about the speed of light, and the interferometer you're using here, what is the differences and what is similar?
Boy, I don't even understand it from you. So, let's start again. Right. Understand. Yes, I can talk to that. But I thought you were asking a different thing, and I will get to that in a second. I failed to mention something very important at the end of the black hole business. I mean, the neutron star business. When you looked at that 1.7 seconds, I thought this is what you were asking, and it's related to it. That 1.7 seconds difference between the gravitational wave hitting us and the gamma rays hitting us, and that thing being 40 million light years away, tells you that the velocity of light is the same for gravitational waves and gamma rays to a part in 10 to the 15. So Michelson-Morley could never measure anything that, but that's a separate code. Now, you ask why about if there is an ether drift. And it doesn't matter. I'll tell you why. And there are people who are proposing using LIGO as a way of doing the Michelson-Morley experiment over again. And I'll tell you why that's become sort of sexy nowadays, is there are new theories for Lorentz covariant and Lorentz invariance. I won't even pretend to understand what the problem is. But I know there are people making that a big industry, and that you could, if you could really see a difference for the velocity of light in different directions, that would have strong implications for something. God knows, maybe you can tell me, but I don't know what it is. But so they come to us and say, can we use LIGO as a way of doing that? And it turns out that you can do no better, I don't think, and the reason has to do with the way we operate the instrument. We deliberately have to hold the instrument against the ground noise. The ground noise is so large that we have to hold the instrument. For those of you who know interferometry, we have to hold the instrument to 10 to the minus 10 of a fringe. We have to hold it, otherwise we lose sensitivity. There are servo systems, there are control systems that hold all the mirrors so that they don't move by more than 10 to the minus 10 of a fringe. That means 10 to the minus 10 of a wavelength in effect, 10 to the minus 15, 10 to the minus 16 meters. Not 10 to the minus 18, 10 to the minus 16. And that gives you a dynamic range of about 100 still, where you can run the instrument and look for signals. Now, we have to do that, otherwise the thing is all over the place. You never hold a fringe. You have no sensitivity. And so it turns out that this same system that does the control of the positions of the mirrors so that they're in the right place to make the interferometer sensitive screws up any long-term thing. Like, for example, you rotating the apparatus over 12 hours or 6 hours to see if there's a difference in the length of the apparatus that you measure with the light. We don't have any sensitivity for that because we actually kill that out by holding the interferometer at that very tight tolerance of the fringes. So we're not a good instrument to do the Michelson-Morley experiment over again. That's what I've been trying to tell you.
Okay, let's thank Rai again.
Yeah. All right. Thank you very much. I see most of you stuck it out, which is sort of wonderful, I must say. I'm delighted.
So we'll follow with refreshments and the poster session outside. So.
I'm going to disconnect the computer, the gentleman who worries about